To practice going from acceleration to position, let's derive the acceleration, velocity, and position functions of time in one dimension for constant acceleration. Okay, we end up working with constant acceleration a lot, and so these will be very useful. But it's still important to know that this is a very special case, that specific case where the acceleration is constant. So we're going to be in one dimension. We're going to call that one dimension the x-axis, and so the acceleration then is along the x-axis. The acceleration is some function of time, but it's just a constant. And so we'll give that constant just a, since it identified as an acceleration, and without any of these other subscripts or the t, since to identify it as a constant. Okay, so if the acceleration is constant, we now want to find the velocity. So the velocity is an antiderivative of the acceleration. So that's the antiderivative of a constant, which is just a times the time plus then some additive constant c. Okay, so we can find what that is by evaluating the initial conditions, which is the value of this velocity function at t is equal to 0. Well, that is this additive constant c, since this term is 0. If we identify this as the initial velocity, which we call v sub x naught, then we have our new velocity as a function of time, which is equal to v subscript x naught plus acceleration times time. Okay, fine. Now let's find the position. The position as a function of time is now going to be the antiderivative of the velocity function of time. So that's equal to this constant, the initial velocity, times time, plus the antiderivative of this term, which is then 1/2 a t squared plus some additive constant. And we can find that constant by the initial conditions, which is the value of the position function at t is equal to 0. Well, this is 0, that's just the additive constant c, and so we give that a name. The initial position we often call x naught. So there we have now our final position as a function of time, which is the initial position plus the initial velocity times time plus 1/2 times the acceleration t squared. Okay, so these are the functions. They're vector functions of time for the acceleration, velocity, and the position. They tell you at each point in time what the acceleration, velocity, and position vectors are. And so if we were to, let's look at a graphical representation of what these might look like. So if I have some positive acceleration that's some constant, say I have a car that's accelerating, so this is a of t, it has some constant positive acceleration. To get my velocity, I have to know what my initial condition is. So let's say I have some initial velocity equal to 0. Then my position function, my velocity function, would be equal to, as a function of time, is equal to at, so it's some increasing straight line. So this is v of t, and then finally, what does my position look like? Well, that also depends on where it starts. Let's say my initial condition my initial position was equal to -5 meters, and so my position function of time would be -5. Initial velocity was 0, so plus 1/2 a t squared. So it starts at some negative value, and I get a positive parabola up. Okay. So anyway, so these are what the constant velocity graphical representations look like. Acceleration is a constant, then the velocity is going to be some straight line where the slope is given by the value of the constant acceleration. And then the position function of time will be some parabola that is given by the acceleration as well.